Syntax builds the form we see. Semantics gives it meanings key. Connectives link what minds devise. Quantifiers range through truth and lies. Modus ponens strikes with might. Modus tollens flips the fight. Logic cuts clean, no shallow line. Through the long night, reason shines.
Previously, we have discussed how to use connectives to combine individual logical propositions into compound ones. This greatly enriches the kinds of logical propositions that we can make. However, nothing is said yet for the truth values of these compound propositions. In this session, we discuss how to determine the truth value of a compound proposition based on the truth values of its simpler components. The main tool we use is the truth table. A truth table is a chart that lists all possible truth value combinations of the atomic propositions involved and shows the resulting truth value of a compound proposition under each of these combinations. Each row corresponds to a specific assignment of truth values, and each column represents either an atomic or compound proposition. We first present the truth tables for compound propositions involving only one connective. We will also discuss subtle differences in how these connectives are interpreted in logic versus everyday English whenever necessary. We start with negation. Not P is true when P is false, and false when P is true. In other words, P and not P always have opposite truth values. For conjunction, P and Q is true only when both P and Q are true. In all other cases, it is false. For disjunction, P or Q is false only when both P and Q are false. Otherwise, it is true. We remind the reader that in everyday English, when someone says, "I want to be a doctor or a lawyer in the future," the word "or" typically implies an exclusive choice, one or the other, but not both. In logic, however, the disjunction "or" is inclusive. As we can see from the truth table, the statement P or Q is considered true if at least one of P or Q is true, including the case when both are true. For the implication, if P, then Q is defined to be false only when the antecedent P is true, and the consequent Q is false at the same time. In all other cases, it is considered true. In particular, when the antecedent P is false, the implication is regarded as true regardless of the truth value of the consequent Q. Some students might feel reluctant to accept this convention at first. However, it is important to remember that we are discussing logical implication, not causal relationships. The implication simply defines a compound proposition whose truth value is assigned according to the truth table. It should not be interpreted as stating that P is the cause or reason for Q. For example, if 1 is greater than 0, then a cat is a cat. This proposition is considered true because both the antecedent and the consequent are true. However, clearly 1 is greater than 0 is not the reason why a cat is a cat. Although this may feel unnatural initially, such a convention often brings convenience when working with logical deductions, which will be explained later. Finally, the equivalence P if and only if Q is true when P and Q are both true or both false. If the truth value of P differs from that of Q, then the proposition is false. We strongly recommend that the audience become familiar with the results presented in these basic tables. With these basic tools in hand, we are now ready to move on to the next section and analyze the truth tables of compound propositions with more complex structures.
신라 텐세